Hello students, I'm Dr. Himani Sharma from the Department of Physics, Doon University. Welcome to the third module of the course Analog System and Applications. In the last module, we studied about the PN junction diode and their VI characteristics. Apart from that, we also studied about the diode as full wave and half wave rectifiers, what is the concept of ripple factor and how these diodes are used in various applications. So in continuation to that, we are going to study about the efficiency of the rectifiers and how these are being used as Zener diode, light emitting diode, photodiodes and solar cell. So we are starting with our third module of this particular course, analog system and applications. The description of the module is as such. The name of the paper is Analog System and Applications and the title is PN junction diode and applications. The content of the module are efficiency of rectifier, Zener diode as voltage regulator, light emitting diode, photodiode and solar cell. The learning outcomes from this module are efficiency of a full wave rectifier, Zener diode and voltage regulation, concepts of light emitting diode and photodiode, solar cell. In the end of the module, you are provided with the quiz. You may go through the module and try to solve that quiz. So we are starting with our third module. In this module, we are starting with the rectification efficiency of a rectifier. What is the rectification efficiency? Efficiency of a rectifier is defined as the ratio of the output DC power to that of input AC power, which is given by the symbol beta. So this is a definition that if you have calculated the DC power to the load and the AC power from the transformer, and you may calculate the efficiency of a rectifier. So if we calculate the efficiency of a rectifier, it is given as 40.6% for the half wave rectifier and 81.2% for the full wave rectifiers. So these calculations assume an ideal diode, no voltage drop across the diode is being considered and no reverse leakage is being considered here. So in real world applications, the diode characteristics would slightly affect these values. So from here we may see that the efficiency of half wave rectifier is 40.6% and that of full wave rectifier is 81.2%. So which shows that a full wave rectifier is highly efficient in converting the AC to that of DC in comparison to the full wave rectifier. In our last module, we also discussed about the ripple factor. So ripple factor in case of the value of the ripple factor in case of half wave rectifier is 1.21. However, this particular value is 0.48 in case of full wave rectifier. So it also shows that the full wave rectifier is better than that of the half wave rectifier in various studies. Coming to Zener diode, it has already been discussed that when a reverse bias on a crystal diode is increased, a critical voltage called breakdown voltage is reached when the reverse current increases sharply to high value. The breakdown region of the knee of the reverse characteristic is shown in this particular figure, which basically corresponds to the Zener diode. Zener diode are special type of diode designed to operate in the reverse bias mode. It basically is a properly doped crystal diode which has a sharp breakdown voltage, which is known as a Zener diode. So if you see this particular VI characteristics of a Zener diode, so this right hand side, if you see, this is a Zener diode. This is a circuit of a Zener, or symbol of a Zener diode, where this arrowhead corresponds to the P, and this Z shape uh, element, it basically shows the inside of a diode, which basically makes it as a Zener diode. So if we connect the Zener diode and make a complete circuit, so in the forward side, when you connect the P side to the voltage of the positive terminal of the battery. So it will result in the forward biasing as shown in this figure. But on the reverse side, you will find on the increase of the voltage in the reverse biasing, you'll find a point which is known as the a sharp breakdown voltage. Sharp breakdown will be here this at this particular point, and there will be the when you keep on applying the reverse voltage, there will be the sharp rise in the current in the reverse direction. This particular knee point in the reverse direction is known as the breakdown voltage, which corresponds to the and make a particular diode as a Zener diode. So this junction was first given by American scientist C. Zener. Therefore, the breakdown voltage sometimes is called the Zener voltage, and the sudden rise in the current is known as a Zener current. So when you keep on rising, when you keep on increasing the voltage in the reverse directions, corresponding to that, the current will also rise, and there will be the sharp rise in the current, which corresponds to the Zener current. A Zener diode is like an ordinary diode, except that it is properly doped, so that as to it has a sharp breakdown voltage. It always works in the reverse biasing, and the Zener diode is always reversely connected. It is always a reverse bias diode. So Zener diode always works in the reverse biasing. Zener diode has a sharp breakdown voltage, which is called as the Zener voltage. The Zener diode is not immediately burnt just because it has entered the breakdown region. As long as the external circuit connected to the diode, it limits the diode current to less than burnout value. The diode will not burn out. So this is the basically we may say that it helps in basically protecting the burning out of a Zener diode in the reverse biased region. So if we see the equivalent circuit of the Zener diode in the next slide, in this slide we are going to study about how a Zener diode acts as a voltage regulator. A Zener diode is used as a voltage regulator to provide a constant voltage from the source, whose voltage may vary over sufficient range. If you see the circuit arrangement, so we have shown here the figure 1 and figure 2, which basically shows how a Zener diode can act as a voltage regulator. The Zener diode of voltage Vz, so this is the voltage Vz, which is reverse connected across the load, and which is a constant output from where we have a constant output, the one we desire. The series resistance R absorb the output over voltage fluctuation so as to maintain the constant voltage across the load. So it may be seen that Zener diode will maintain a constant voltage Vz across the load as long as the input voltage does not fall below Vz. When the circuit is properly designed, the load voltage E0 remains constant, which is equal to Vz, even though the input voltage Ei and the load resistance may vary over the wide range. So here we have the two cases. The first case is the voltage that we have applied, the reverse voltage, it has to be greater than or equal to this Vz so that your Zener voltage can act as a voltage regulator. But if this voltage is lesser than the Vz or greater than 0, then this Zener diode does not act as a voltage regulator. So suppose the input voltage increases and the Zener diode is in the breakdown region. The Zener diode is equivalent to the battery Vz as can shown in this particular figure 2. It is clear that the output voltage remains constant. So the voltage that is being which is there across the Zener diode, it remains constant even when you have the excess voltages drop across this particular resistance R. So this will cause an increase in the value of the total current. The Zener will conduct the increase of current in I while the load current remains constant. Hence, the output voltage E0 remains constant irrespective of the changes in the input voltage. Now suppose that the input voltage is constant but the load resistance RL increases. So what you have done now, you have made the change other way. So initially you were increasing the voltage, now you have kept the voltage constant, but your this load is being increased. This will cause an increase in the load current. The extra current cannot come from the source but drop in R. So there will be the voltage drop across the resistance here in this particular resistance R, and it will not change as the Zener is within its regulating range. So the additional load current will come from the decrease in the Zener current. Consequently, the output voltage stay at constant value. So voltage drop across R can be shown from this particular equation, that is EI minus E naught, which is being shown here. And the current through the resistances can be I is equal to the Zener current plus the load current, which will come out to be the total current, and hence R can be calculated from the Ohm's law, which is basically V upon I. So this is your the voltage from this circuit, and you will be having V upon I, which will give you the value of the resistance. The next application of the diode is light emitting diodes. Light emitting diode is basically a semiconductor device that emits light when the current flows through it. Unlike incandescent bulbs, which produce light through the heating of the filament, LED produces light through the phenomena of electroluminescence. So how does it basically work? So the principle of operation is like that. It basically is the electroluminescence process. LEDs operated based on the principle of electroluminescence. When a suitable voltage is applied to the terminals of an LED, electrons recombine with holes within the device, releasing energy in the form of photons. This process then produces light. It also depends upon what is the band gap of that particular semiconductor. The color of the emitted light by a LED is determined by the band gap energy of the semiconductor used in the diode. Different materials emit photons of different energy, which translate to different colors in the visible spectrum. The characteristic of this particular LED are basically depends upon this efficiency, longevity, and fast switching. So this is a symbol of a light emitting diode, which basically show a PN junction, and it's this arrow corresponding to the emission of light, and LED always work in the forward biasing. So if we talk about their characteristics, so LEDs are more efficient than incandescent and more fluorescent lights. They produce more light per watt of electricity consumed. They have high longevity. LED typically have longer lifespan, often lasting 25,000 to 100,000 hours, significantly more than the traditional lighting solutions. They have fast switching. They can turn on and turn off very rapidly, which makes them ideal for applications like optical communication and displays. They have a color range. They can produce a wide range of colors without using filters, making them more efficient for colored lighting applications. They have low heat production, unlike incandescent bulbs, which waste more of their energy as heat. They are cool to touch. They have high voltage sensitivity and require specific forward voltage to operate, and are sensitive to voltage fluctuations. LEDs emit light in a specific direction as opposed to the incandescent or the fluorescent bulbs, which emit light in all the directions. So basically how a particular light emitting diode works, it is basically made up of a semiconductor light emitting diode, which has and a semiconductor diode, as we know, is consist of two type of materials, p type and n type. N type has excess electrons and p type has excess hole. So when a p-n junction is formed, there will be P and N type materials are joined by a certain process, and a PN junction is being formed, which is the central region for the emission of light. And LED always works in the forward biasing. It means when the voltage is applied with the P side of the material. So if this is a P side, this particular side is the P side, this particular side is the N side. So when voltage is applied with the P side positive, and electron from the N side, uh, so there will be the movement of electrons from the N side, and they'll go towards the PN junction. So this is the junction where the electrons will move, and holes from the p side to the same. So this is how their movement will take place. And at the junction they'll recombine. The recombination of electron and hole will take place. So this is a junction here, electron coming from here, holes coming from here, recombining here. So at the junction, when the recombination will take place, electrons fall into the holes, and that process leads to recombination. So when the recombination takes place, it leads to the emission of light. The recombination process releases energy, and that energy which is being released, that is nothing but the light photons, or the light is being emitted, and the color of the emitted light depends upon the semiconducting material, the band gap of the semiconductor basically. So it decides what kind of wavelength is being emitted when the recombination takes place. So this is how LED is being uh, how the operation of a LED takes place. There is a formulation for that. Hc upon lambda is equal to Eg, where lambda is equal to Hc upon Eg. Eg is the band gap and lambda is the wavelength of light, and lambda is given as 1241 upon Eg nanometer, which basically gives us either the band gap or wavelength of that particular light. So this is how our LED works. Coming to the next slide, which talks about diode as photodiodes. Photodiodes are basically the semiconductor devices that converts light into electrical current. It is a form of light sensor that converts light energy into electrical energy, that is basically using voltage or current. It is a type of semiconducting device with the p-n junction between the p positive and n negative layers. An intrinsic layer is present, so that we already know that we have an intrinsic layer in between. The photodiode accepts light energy as input to generate electric current. It is also called as a photodetector, photosensor, or a light detector. Photodiode operates always in reverse bias conditions. That is, P side of the photodiode is connected with the negative terminal of the battery, as can be seen in this particular figure, and the N side is connected to the positive side of the battery. So this is the symbol of a photodiode. And the typical photodiode materials are silicon, germanium, gallium arsenide phosphide, and indium gallium arsenide. So these are the example of a photodiode. So how a photodiode basically works. Generally, when a light is made to eliminate the p-n junction, so what will happen, because it is reversely biased, so covalent bonds are ionized. This generates hole and electron pairs when the covalent bonds are broken. So we'll be having electrons and hole pairs are being generated. So these photocurrent, because of that, you'll be having photocurrents are produced due to generation of electron hole pairs. Electron hole pairs are formed when photons of energy more than 1.1 electron volt hit the diodes. When the photon enters the depletion region, so when the light is entering into the depletion region of the diode, it hits the atom with high energy. This results in release of electron from atom structure, from the particular atomic structure. After the electron releases, the free electrons and holes are being released. So this is how, when the light is impinged on the reverse bias p-n junction, it basically generates the electric current. This is the VI characteristics of the photodiode. It always, as already discussed, it operates in the reverse biasing condition. Reverse voltages are plotted along the X and Y axis, as can be seen here. So on X axis we'll be having the voltage and reverse current are plotted along the Y axis. So we have the voltage here and we have the current in the Y direction. Reverse current does not depend upon the reverse voltage. So when we haven't applied any light to a particular diode, so whatever the current which is coming from the diode is basically known as a dark current, because we haven't applied any light. But when the light is being impinged on the diode and when there is illumination of the diode by of certain wavelength, so there will be the rise in the reverse current. But when no light is there or the dark current is there, so at that particular point the reverse current will almost be zero, which is known as the dark current. The minimum amount of current, so that particular amount of current is known as the dark current. But when the light is being impinged or the diode is being illuminated, so reverse current keeps on increasing, as can be shown in this particular figure. So reverse current is increasing rapidly. So here we can see, we can see in this particular picture, when the intensity of 1000 lux, 1500 lux, 2000 lux and 2500 lux is being applied on a diode, how the current have been increasing has been shown here. And here we haven't provided any illumination, so this is a dark current, so which is also showing the image on the left hand side. So a very small current is there when no illumination is there. But when the diode is being illuminated with a certain amount of light intensity, so this is seen how there is a rise in the current on illuminating. So this is the property of the diode in the reverse biasing that is used for various applications. So what are the applications of photodiode? Photodiode are used in many simple day-to-day applications. So they are being used for as photosensors. They help to provide an electric isolation with the help of optocouplers. When two isolated circuits are illuminated by light, optocouplers is used to couple the circuit optically, but the circuit will be isolated electrically. So compared to conventional devices, optocouplers are fast. Photodiode are used in safety electronics like fire and smoke detectors, so that can be that are basically used in various buildings, hospitals, universities. So when you have certain amount of smoke, then it will start blinking, and so it can detect that smoke and start blinking, or some alarm will come out from there. So it is basically used for detecting the smoke in certain buildings, or where certain safety conditions are needed, and also used in the UV unit, so TV unit. So this is how the photodiodes are being used for various applications. So the next application of PN junction diode lies in the area of the solar cells. So solar cells are basically semiconducting devices that convert sunlight into electrical energy or the electricity. With the increasing demand for renewable energy, the significance of solar cells has grown exponentially. They serve as the primary units in solar panels, which are used for a variety of applications ranging from pocket calculators to large solar farms. This is a symbol for solar cell, which shows the light is being incident on a particular system, and that converts one form of energy into that of another. So construction of solar cell can be seen in this figure, where we have a p-type silicon layer on one side and n-type silicon layer on the other side, and which are being coated with the metal coating layers. So we have one coating here and the other coating here, and these coatings are anti-reflecting coating. These electrodes, they do not obstruct light to reach the thin p-type layer. Just below the p layer there is a p-n junction, which also provide a current collecting electrode at the bottom of the n layer. This particular construction is being encapsulated by a thin glass, so that this cell can be protected from the mechanical shock. So how a solar cell basically works. When a very thin layer of p-type semiconductor is grown on a relatively thicker n layer, a fine electrode is placed over p-type layer. The layer is such that it doesn't obstruct the light, that I already discussed in the previous slide. A current collecting electrode is provided at the bottom of the n layer, and further we just encapsulate in a thin glass to protect the solar cell from the mechanical shock. When the light basically reaches the PN junction, as we may see here that we have light when it reached the PN junction. So PN junction is being shown in the earlier slide. Light photon can easily enter the junction through the thin p layer. So that's why we have made the thin layers of small thickness, so light can easily incident through that thin p layer, the light energy supplies sufficient energy to the junction to create number of electron hole pairs. The free electron in the depletion region can come quickly to the inside of the junction. Similarly, holes in the depletion region can come quickly to the p side. After sufficient amount of transfer of the carriers, no more carriers can move because of potential difference. As the concentration of electron holes become more in their respective sides, the PN junction will behave like a small battery cell. A voltage is being set up which is known as the photovoltage. So if we provide or connect a small load across the junction, there will be a tiny current flows through that particular circuit. So this is how a solar cell works. So first of all, we have photons with energy. That energy has to be greater than the band gap of the semiconductor, so that when it incident on that semiconductor, it excites electron from the valence to the conduction band, and this process basically creates the whole electron hole pairs. And by establishing the electric field usually via p-n junction, these electron hole pairs are generate that basically generate a small amount of current, and a voltage is set up which is known as the photovoltage. And on connecting a small load across that junction, a tiny current basically flows across that particular junction, which can be easily measured. And a solar cell also always works in the fourth quadrant of VI characteristics if we want to plot. So if you see the VI characteristics, so this is known as the open circuit voltage, and here we have the short circuit current. This is the photovoltaic, the voltage that we are applying. Corresponding to that, we have the current. The maximum power transfer is given at the maximum voltage at this particular point, and corresponding to that, we have the maximum current which can be taken from this particular point. So this point is known as the point of maximum power point. So corresponding to the maximum current and the maximum voltage, that is V into I, gives you the maximum power across this VI characteristics, and this point is known as the open circuit voltage, and this particular point is known as the short circuit current. So the key components of a solar cell are basically solar cell are made up of silicon, both mono and polycrystalline, which is mainly used material for making the solar cell, although other materials are also being used like gallium arsenide, perovskite cells, which are most researched materials these days, organic photovoltaics, p-n junction, which is being formed by doping two adjacent regions of the semiconductor, one with the positive p-type and another with the negative n-type. And then we have the top and the bottom contacts, depending upon the material with which we are making the contacts. They are basically the metal contacts, and anti-reflective coating which enhances the light absorption and reduces losses due to reflection. So and that's why we have to choose that material which have all these properties to make a particular solar cell. So with this we have completed our third module of this particular course. And after the completion of the module, you are provided with the quiz. You have to solve that quiz, and if you have any queries, you can contact me through the email, and or we may create the Google class link and we can discuss our problems. So thank you so much.